So in this video we're gonna talk about another unsaturated hydrocarbons called alkynes. As we already know, alkynes normally have a formula which is CnH2n 2. The molecular formula. From this formula where n is the number of carbon atoms. Right. So by using this formula you can easily tell whether the molecular formula belongs to the alkyne or some other unsaturated hydrocarbons, and this is characterized by the formation of triple bond, something like this. So if you have triple bond, that means that this belongs to an alkyne. So one of the common example is acetylene. You have carbon carbon, you have triple bond, and then you have one hydrogen attached across the carbon bond, so the carbon will have 4 bond. So now let's talk about, if we talk about the geometry of the acetylene. So again we're gonna use the same rule of orbital diagram. So in acetylene and alkyne, carbon is sp hybridized. What does it mean? The electron from the 2s orbital moves to the 2p orbital, and out of the 4 1s orbital and 3p orbital, when they mix, they just mix 1p and 1s. So that's the definition of sp. One of the s orbital and one of the p orbital is gonna mix together and form 2 hybridized orbital, and then the rest of the 2 is remain unhybridized. And then we'll see how this affects the structure of the alkyne molecule. So if we have hybridized orbital 2, so what does it mean? This is carbon, it has hybridized orbital. One of the hybridized orbital is this, another one is this. Then we have second carbon. In second carbon you have 2 hybridized orbital. One of them is this, second one is this, and each of them has 1 electron. Same thing for green one. First one you have 1 unpaired electron, which is this. Right. Now we have the unhybridized p orbital. The unhybridized p orbital is present perpendicular. This is one of them, this is second one. Same thing is gonna happen over here. This is unhybridized. P orbitals. P orbitals. So what's gonna form once the hybridized orbital is gonna share the electron between carbon and carbon, they're gonna make a sigma bond. So like I already told you about the sigma bond is formed by the overlapping of hybrid orbitals, whereas the unhybridized p orbital is gonna overlap. So if one p unhybridized orbital overlap from each carbon, they're gonna make 1 pi bond. But in this case we have 2 unhybridized orbital on each carbon, and if they overlap with each other, they're gonna make 2 pi bond. So the structure will be like this: C, single bond, C, then you have hydrogen attached, and then this is your sigma bond made by the overlapping, and then you're gonna have a pi bond, which is one is on the top, one is on the bottom. This is pi bond formed by the overlapping of unhybridized p orbital, right? So we know that out of the 3 bond, 2 are pi bond, one of them is sigma bond, And if I talk about the hybridization of the carbon, what is the hybridization state of carbon? Can I say sp? Yes, because out of the 4 bonds this carbon has 1, 2, 3, 4, only 2 are formed by what? Hybridized orbitals. And what are those hybridized orbitals? One from the s, one from the p. So that's why you have sp. Similarly, for this carbon, what is the hybridization state for this carbon? So out of the 4 bonds, we have just 2 bonds from the hybridized orbital. And what are the hybridized orbital? One is s, one is p. So sp. So make sure you know how to figure it out, the hybridization orbital for alkane, alkene and alkyne. So now let's try to solve or try a couple of problems regarding the hybridization state of the carbon. So let's take an example. You have CH, H, C, H, H and H. Then you have second molecule, double bond, H, and then the third one, triple bond, H, H and H. So if the question asks you what's the hybridization state of each and every carbon in all the 3 molecules, so how are you going to figure it out, the hybridization state? Hybridized state of carbon for each of the 3 compound, 1, 2 and 3. So now let's see that example over here. So you have to see only the single bond. So let's say on carbon compound 1, carbon number 1, carbon number 2, you have to figure it out how many single bond you have in there. On carbon number 1 you have 1, 2, 3, 4. You have 4 single bond combined with the carbon. So that means you are using 4 orbital. You have 4 bond, 4 single bond, means you are using 4 orbital. So one of them is s, another one is, the other 3 should be p orbital. So the hybridization state is sp3 for first carbon. What is the hybridization state for the second carbon over here? Again, you have all 4 single bonds. If you have 4 single bond, that means you needed to have 4 hybridized orbital. So that means if you have 4, 1 from s, 3 from p, so 3 plus 1, 4. So this carbon also has sp3. Now let's talk about the second structure, and you have to tell me what's the hybridization state for each of the carbon 1 and 2. So how are you going to determine? So again, you have to see the single bond only. So on the first carbon, how many single bond you have? 1, 2, 3, and out of the 2 bond that you have, one of them is pi bond, which is not sigma bond, right? So you have to see the single bond, or you can say a sigma bond only, right? So out of the 4 we have 3 sigma bond. So that means we have 3 hybridized orbital, because sigma bond is formed only by, or single bond is formed by hybridized orbital only. So s, p, 2, because we have 3, so 2 from the p orbital, 1 from the s, so total is 3. 2 plus 1, 3. Same apply for this carbon, 1, 2, 3. One of them is pi bond. We don't care about pi bond, we have to just see the single bond, sp2. So 2 plus 1, 3 single bond. Similarly for alkyne, the triple bond was the hybridization state for out. So this carbon has 4 bond. Out of the 4 bond, only 2 are single, because top and bottom are pi bond. We are not going to consider the pi bond, we are going to consider just the single bond. So we have 2, that means this carbon needed 2 hybridized state or hybridized orbital. That means one is s, one is p. Same apply for this sp. Out of the 4, 2 are single bond, other 2 are pi bond, right? So this is how you normally going to get the hybridized state for any carbon in any molecule. So let me give you one more example. So if I ask you what's the hybridization state for carbon number 1 and carbon number 3, so how are you going to solve this problem? So carbon number 1 has a hybridization state of what? sp, sp2 or sp3. So which hybridization state carbon will have right now? So let's see on this carbon how many bonds this carbon have. 1, 2, 3, but where is the fourth bond? I cannot see it. The fourth bond is the hydrogen. Like I already told you, the line angle formula don't show you the hydrogen, so you have to assume the hydrogen is still there to make the carbon 4 bond, right? So how many single bond you have? One single bond is over here, second one is here, third one is with the hydrogen, because this double bond is a pi bond, right? So this carbon has 3 single bond. That means you have to have 3 orbital, hybridized orbital, means 1s and 2 comes from p. So 2 plus 1, 3 total. So carbon number 1 has sp2 hybridized state. What about carbon number 3? So again, this carbon has 4 bond. One single bond is here, second single bond is here, and then you cannot see 2. There is 2 hydrogen because each carbon has to have 4 bond. So it has 4 single bonds, right? So this carbon number 3 has sp3 hybridized state, because they need 4 hybridized to make 4 single bond. 3 comes from here, 1 comes from this, that's 4. So this is how you normally figure it out, the hybridized state for any carbon, if you get any problem in the exam. So now let's try to learn about nomenclature of alkyne. You already done alkane, you already done with alkene. Now you have to do for alkyne. You have to use the same rule like you used for alkane and alkene, but the only difference in there, in alkene you have to give the priority to the double bond. Here exactly the same. Instead of double bond, you have to give the priority to the triple bond. You have to include the triple bond in your longest chain, longest parent chain. You cannot leave the triple bond outside the parent chain, and you have to give the preference to the triple bond. Doesn't matter where the substituent is, as long as you are getting a lowest number on the carbon that has a triple bond, you're okay. So now let's try to name this molecule. So you have 1, 2, 3, 4. You have 1, 2, 3, 4. I started from right to left because on the first carbon you have a triple bond. That's why I have to give the lowest number to the carbon that has a triple bond. So this is 4 carbon, this is but, and then the ending word, make sure the ending word will always be "ine," comes from alkyne. So is 1 butyne. 1 means triple bond is present on the first carbon, and that has, the parent chain has 4 carbon altogether, so is butyne. Similarly, on the second example that you have over here, we have to start counting from this side. 1, 2, 3. Either you can go down 4 or you can go all the way straight 4. So I would suggest you always go to the straight line, but even though if you're going to get 4th on this carbon is still okay, but we are going to get the straight chain, parent chain, and that parent chain also included the triple bond, and we already gave the lowest number to the carbon that has triple bond. So this is your substituent. This is methyl, so the name will be 3-methyl. On the first carbon you have ine, butyne, because this is 4 carbon and you have triple bond on the first, so 1-butyne. Or instead, if you just write 3-methyl butane is also correct, even though if you don't write 1. So if you don't write 1, we assume this is on the first carbon. So let's try to solve some more problem naming of alkyne. So let's try to solve this problem. This is a line angle formula. This is a triple bond. You have chlorine over here. So let's try to name this molecule or this organic compound. The time I see a triple bond over here, we know this is an alkyne. So we have to start counting from this side, from right to left, because we have to give the preference to the triple bond, and then second is the lowest one, because if we would have started from this side, we won't get the lowest number on the triple bond. So we have to keep our numbering from right to left, and then 3, 4, 5, 6, 7 and 8. So how we normally name this molecule? So we're gonna write 7-chloro, then we have 8, but before 8 we have to write the location of the triple bond, which is 2, then 8 is oct, and then YNE, because we have a triple bond. So 7-chloro 2-octine, or we can write the same thing as 7-chloro oct 2YNE. As long as you are specifying the location of a triple bond, the name is right. So both are correct. So now let's try to solve one more. Chlorine. So now let's try to solve this this molecule, or the name of this organic compound. The time I see is a triple bond. We know this is an alkyne. Now we have to start counting the longest parent chain. So either we can start from left to left, or we have to start from left to right. So which way we have to start count? So if we start from right to left, let's say 1, 2, 3, 4, 5, 6, we are having a triple bond on the third carbon. So let's count the other way around. If we start from here, 1, 2, 3, 4, 5, 6, again we're going to have a third location of the triple bond. So there is a tie, so it doesn't matter which way we have to start, both ways we are going to get a triple bond on the third carbon. But we have to still decide which, and we have to start count. Now we have to see, this is our parent chain. We have two substituents, this is chloro and this is methyl substituent. So now if we find if we try to figure it out, which end we have to start count, by looking at the substituent we still cannot figure it out, because on each side the substituent is present on the second carb, if you can see. So there is a tie on the substituent also, as well as on the triple bond. So how are we going to decide which one we have to count? Now we have to choose alphabetically the name of the substituent alphabetically. So the chloro comes first in front of the methyl M, so we have to start counting, because the C comes alphabetically earlier than M. We have to start counting from left to right. So that means our yellow marking is the correct numbering system for this particular structure. So I am going to take out the red one. And then the name will be chloro five methyl 3, and then you have 6 hexane, or you can write the same name as 2-chloro 5-methyl hex 3-ine, because you have to specify the location. So make sure you practice all this type of question of naming any organic compound whether it's alkene. Now let's talk about the properties of the alkyne. So physical property are similar to alkane and alkene. They are insoluble in water, less dense with water, and have low melting and boiling point. And for the chemical property, alkynes show exactly or similar properties like alkene. They can do addition reaction and they can react with Br2, which is halogenation reaction. This is hydrogenation reaction. This is halogenation reaction. So alkyne can show all the type of addition reaction or similar type of reaction that alkene does. But we are not going to show how does it react with all of them. Okay, so now let's talk about the aromatic compound and aliphatic compound. What's the differences? So aromatic compound which contain the benzene ring. Aromatic compound normally contain the benzene ring or is structural relative. So what is benzene ring? Benzene ring is a hexagonal carbon, 6 carbon cyclocarbon with alternate double single double bond. This is your benzene. This is the structure of benzene. And if we have to see actually the carbon, this is a line angle formula. But if we actually have to see the carbon and hydrogen, if we can see on this structure, you have carbon, you have 6 carbon, 1, 2, 3, 4, 5, 6, and then if you can see carefully, you have alternate double single double bond, alternate double single bond, right? And then aromatic compound has low hydrogen to carbon ratio, means it has less hydrogen compared to the other hydrocarbons. Okay, so if I ask you about over here, so if I ask you about what is the hybridization state for this carbon, how are you going to determine what's the hybridization state? Again, the same principle. You have how many single bond? 1, 2, 3. So to make 3, you need 3 hybridized orbitals. So sp2, 2 plus 1, 3. So make sure we already know about how to figure it out the hybridization state. So what is aliphatic compound? Aliphatic compound are those organic compounds that are not aromatic. So all those compounds that are not aromatic, that doesn't have a benzene ring, are called aliphatic carbons or organic compound. This include alkene, alkane, and alkyne. So now let's talk about the structure of a benzene. Like I already said, benzene is a hexagonal with alternate single and double bond. This is the property. So if you see over here, 1, 2, 3, 4, 5, 6. If we count this one, the numbering like this, if we see the double bond between 1 and 6, now the double bond is disappear between 1 and 6 and goes to 6 and 5. So it's like this. So that means this confirms that the double bond is keep on changing its place within the structure of benzene, right? So that's why most probably you will see this kind of structure of benzene with a 6 carbon close ring and a circle in the center. This circle represents the double bond is keep on changing its place within the benzene ring, and then they are changing so fast it's very hard to determine where the double bond is at that period of time. So they normally show a circle. That means the double bond is keep on changing its position, right? the structure of benzene. So each carbon in the benzene ring has 3 sp2 hybridized orbitals and 1 hybridized p orbital. What does it mean? It means if you have a benzene, double bond, single bond, double bond, single, double bond, single bond. So if we talk about this carbon over here, this carbon has 1 hydrogen and 1 bond is here, 1 bond is here, and 1 bond with double bond, right? So this carbon is sp2 hybridized, and this pi bond, this carbon has 1 pi bond, unhybridized pi bond, if you remember, p orbital. That's why you have a pi bond over here, the double bond. As we remember that I told you that only the unhybridized p orbital can form a pi bond, right? That's why you have one unhybridized p orbital, right? So this is sp2, this carbon is also sp2, means it has one unhybridized p orbital. This carbon also has one hybridized, this carbon also has one unhybridized p orbital. So out of the 6, all 6 has one unhybridized p orbital. So if we go to the next slide, you will better understand what I am talking about, right? So this is the carbon. This is 6 carbon, 1 2 3 4 5 6, and then this is a carbon, this is a benzene, 6 carbon, single bond, and one of the bond is with hydrogen, right? And this is unhybridized p orbital. This is unhybridized p orbital on each carbon, so they're gonna make overlap with each other, right? And they're gonna make one conduit, something like this, a closed circular conduit where the electron can easily move. And that's why the double bond is keep on changing its place within a benzene ring. And then they are changing so quickly because the electron is keep on moving in the unhybridized p orbital, because they are overlapping and they are making a conduit, right? And that's why sometime you will see the benzene with a 6 carbon closed ring and a circle at the center, because the electron is moving so fast within the benzene ring, right? As you can see from here. So now let's try to name and understand how we can name a benzene derivative. So there are a couple of rules that you need to follow before you can name any benzene compound. So the rule number 1 says when a single hydrogen attached to a benzene ring is replaced, the compound can be named as a derivative of benzene. So that means the hydrogen that was present on this carbon is get replaced by this ethyl group. Then the name of this benzene can be used as a derivative. We can write this name as ethyl benzene. That means on benzene ring you have a ethyl group attached. Similarly, if I remove the hydrogen and put NO2 group, this is a nitro group. So we can say nitrobenzene, right? Similarly, if I remove hydrogen with bromine, we can write bromobenzene, chlorobenzene. So benzene is acting as a parent chain. And we are not writing 1 in the front because the carbon that contain the group we treat as this carbon number 1. So remember this thing. This is carbon number 1, and then 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, and then same kind of thing. Okay. Second rule tells some of the common name are IPIC accepted and used preferentially over the other possibility. That means that couple of the compound, benzene compound, are named as common names that can be used as a IPIC name. So if you have a benzene and on the benzene you have a CH3 group, which is methyl group attached, we call that entire compound as toluene. Similarly, if you have OH group on the benzene ring, the entire compound we call as phenol. This entire compound we call as, with an NH2 group, aniline. And for this group is a carboxylic acid group that we're gonna learn later on. So if you have a carboxylic group attached with a benzene, this entire compound we call as benzoic acid. So you have to remember these common names. So if you see benzene with NH2 group, you should be knowing that this is aniline. Same for phenol. So these are some of the common names that you need to remember. So the rule number 3 is when the benzene ring is part of a more complex hydrocarbon, the benzene ring referred to as phenyl group. What does it mean? If you have a benzene ring but the substituent that you are adding is more complex than the benzene ring. Over here you have 6 carbon, but over on the top you have how many? 7. So you have more carbon in the substituent compared to the parent chain, which is benzene. So we treat this benzene now as a substituent instead of a parent chain. That's why it says if the R group, if any group is more complex than the benzene, then benzene group we treat as a phenyl group. So I can write the name for this one is, on the 4th carbon you have the phenyl group attached, 4 phenyl, you have 7 carbon, heptane, right? But the substituent has to be more complex than benzene before we can use this benzene as a phenyl group. The 4th rule says when two groups are attached to the benzene ring, their position can be designated by the prefix ortho, meta and para. So what is ortho, meta and para means? If you have two groups attached to the benzene, let's say in this particular example you have 2 bromine. So one of the bromine is attached to this carbon, we treat this carbon as 1, and the other one, the next carbon to the one, we call as ortho. This carbon, next carbon is your meta carbon, and this is para. So that's why this is called ortho dibromo benzene, means on the ortho position we have bromine as well as on the first carbon we have bromine. So ortho dibromo benzene. So in this case you have this carbon has a bromine and this bromine is over here. So this is ortho, this is meta, this is para. So that's why this is meta dibromo benzene. Over here is ortho, meta, and this is para. So we can write on the para position you have bromine also, so it's para dibromo benzene. So you have to see the first group that is attached to the benzene and where the other group is present, whether it's an ortho, para and meta. And the 5th rule says when 2 or more groups attached to the benzene ring, their position can be indicated by numbering the ring, so to obtain the lowest number for the attachment position. So what does it mean? If you have 2 or more group attached to the benzene ring, let's take this example, and then let's say you have bromine and chlorine, then you have to specify the number on the benzene ring, which carbon on the benzene ring we can treat as carbon number 1. So why we are using this carbon that has a bromine and group attached to it as number 1, not on the carbon that has chlorine? Because we have to we have to use a rule called alphabetically. We have to name it alphabetically. So bromine comes first, then chloro. So that's why we have to give the preference to the bromo in this case. So we can write 1 bromo and 3 chloro benzene. Right. Similarly, on the second example over here, we have 3 chlorine attached to the benzene ring. So we have to number it such a way that all the chlorine will get the lowest number. So if we start from here, 1, 2, 3, 4. So if I count it like this, then 1 and 2 is the lowest number we can get, and then on the fourth carbon we also have chlorine. So that's why 1, 2, 4 tri means you have 3 chlorine atom on the benzene, right? 1, 2, 4 trichlorobenzene. And then on the third example over here, we know what's this one. This is benzoic acid. We just learned in the previous slides that there are some common name for some particular compound or benzene compound. One of them is benzene with a carboxylic acid group attached to it. So the group that is attached to the benzene, we treat that carbon as number 1 carbon. And then now you have to number it such a way the substituent is going to get lowest number. So this chlorine is a substituent, this chlorine is a substituent. So you have to write on the third and fifth, you have chloro means dichloro, 2 chlorine atom attached to the benzene, and then you have benzoic acid, because you have benzene plus carboxylic acid, benzoic acid. So now let's try to solve a couple of problems based on the rules that we learn about the organic compound or aromatic compounds. So the first question is, you have a benzene ring, then you have CH3 group on the top and CH2 CH3 group on the bottom over here. So the time I see CH3 group and a benzene ring, we know this entire thing is toluene. This is a common name of benzene plus CH3 group. Then we have to specify the toluene group, the CH3 group over here as number 1, that we use as a parent chain. Then you have to count it this way: 1, 2, 3, 4, 5, 6. Then this is 3-ethyl, this is ethyl group, 3-ethyl toluene, which is toluene is your parent chain. Right. Similarly, if we go to the second, you have this substituent which is propyl. This is your benzene. So you write propyl benzene. That's your name for this particular compound. So let's try to solve a couple of more examples. This benzene. So if I have this compound, NH2 Cl. So what should be the name for this compound, benzene containing compound? So the time I see NH2 group and the time I see you have a benzene, I know this entire thing has a name, common name called aniline. If you go previously a couple of slides, you will see the common name for benzene with NH2 group, which is aniline, and we call this as a parent chain. Right? And then you have to specify that carbon that is included in your parent chain that has the NH2 group. So 1, make sure you always start from that functional group that gives you the common name. In this case, NH2 is the common name that's giving the aniline the entire structure. Right, the name for the entire structure. So this is 1. Now you have to think whether you have to go clockwise or counterclockwise in numbering. If I go over here 1, 2, 3, 4, 5, 6, then the substituent is going to get 3 and 4. But if I would have gone opposite way, 1 2 3 4, now the first substituent is gonna come at number 4, which is wrong because we already got the lowest number of the substituent 3. So the right counting is the green one, which is we already did first time. So I'm going to remove the counting over here, and the naming for this compound will be 3,4 dichloro aniline. Let me give you one more example. This is your benzene. You have OH group, you have bromine, and you have chlorine. Okay, so what should be the name for this organic compound? The time I see OH group and then the benzene, I know the benzene with an OH group, they have a special name, common name called phenol, which is our parent chain. So we have to give the carbon that contain the OH group as our number 1 carbon. Now we have to figure it out which way we have to start counting, clockwise or counterclockwise. So we have, let's say so 1 2, let's go clockwise, 3 4 5 6. So the first substituent is occurring on the 3rd carbon and the second one is occurring on the 5th carbon, right? And if I go the counterclockwise, 1 2 3 4 5 6, again our first substituent is occurring on the 3rd one and the second one is occurring on the 5th one, which is same from the previous counting or previous numbering. So there is a tie. So how are we going to break the tie? So now you have to see out of the 2 substituent, which is bromine and chlorine, which one comes first alphabetically. So bromine is gonna come alphabetically first in naming, so we have to give the priority to the bromine in this particular case. So in this case we have to go clockwise, and then the yellow numbering will be the right one in this particular case. So I'm going to take out the blue numbering, right? So the name will be 3 bromo 5 chloro and then phenol. So this is the name for this compound. So make sure you practice about this kind of compound of benzene, and then practice as much as you can for this compound. So now let's talk about the properties of aromatic compound. What are the different properties that aromatic compound shows? About the physical property, they are non-polar as usual because they are organic compound, insoluble in water, and hydrophobic. Hydrophobic means hydro means water, phobic means phobia. So they don't dissolve in water, right? They're same as insoluble. Regarding the chemical properties, aromatic compounds are chemically stable and often remain intact during reaction. So they are not as chemical reactive as alkene was. Even though benzene has alternate double single bond, even though they have 3 double bonds in its structure, still is not as chemically active as alkene is, which has a double bond. Benzene does not go under an addition reaction. This is one of the reactions that normally goes or shown by an alkene, but benzene doesn't show an addition reaction. This is important. Even though they have a double bond, they don't show addition reaction like alkene. But benzene can undergo substitution reaction in which the ring hydrogen is replaced by some other group. Like we already done this thing. Sometime you will have OH group. Sometime one of the hydrogen is get replaced by NO2 group. So these are called substitution reaction. So that means you are substituting hydrogen with something else. In this case OH and an NO2 you are substituting.